Now comes to the our main topic, that is the ultimate strength design of beams, that is the demand of modern era or the present scientists and authors, almost even the ACI code, all codes are now following the ultimate strength design approach. In this approach, I have also discussed in my previous lectures. Strength design method is based on the philosophy of dividing the factor of safety in such a way that bigger part of factor of safety is applied on the loads and the smaller part of factor of safety is applied on the material strength. Okay, that is, I have also discussed in the previous lecture the same statement written here. Now we will start discussing one by one the ultimate strength design approach. Okay. Here is a stress strain behavior of concrete. Okay, here on the vertical axis stress and the horizontal axis strain. Okay, here the concrete FC prime, ultimate FC prime. Here is the crushing strength 0.85 FC prime. When we take the average under the curve, for example, we will take the area under the curve. Okay, area under the curve, that will be stress, and divided by strain here. Average stress, that will be area under curve, okay, divided by 0.003 strain. We will get the average stress. Okay, average stress. Or you can also just think like this is just a thread or line. You have just push it down and make it horizontal. Okay, this F average, area under curve divided by 0.003. Okay, if FC prime is less than or equal to 30 megapascal, then F average comes 0.72 FC prime. How this is determined? This is basically comes from different experiments, researchers guides. Okay, the F average come if the FC prime of your concrete is less than or equal to 30 megapascal, then F average will be 0.72 FC prime. Okay, so now what is the factor between the crushing strength and the F average? Average strength is 0.72 FC prime and the crushing strength is 0.85 FC prime. Beta 1, that is 0.85. Why did we calculate that? For the calculation and for the derivation, the most prominent person, that is Whitney. Okay, Whitney is a scientist who developed the philosophy and the derivation for the calculations of the concrete members. Okay, so for that purpose we use beta 1. Okay, that is the average strength divided by crushing strength, that is a beta 1 0.85. Okay, ultimate strength design of beams. Here again the first step is the concrete cross section with reinforcement. H is the height of the beam, B is the width of the beam, and D is the effective depth of the beam. What is the effective depth of beam mean? It is the from the neutral axis centroid of the steel bars or the reinforcement to the top fiber. The distance between the top fiber to the centroidal distance from the center of the bars, center of the steels, that is the effective depth. Why it is called effective depth? Because when concrete when cracks appear in the concrete in the tension side we ignore, then the only member which take the tension, that is the steel. So that's why this depth is called effective depth. Okay, because steel is the main member which take the tension. The second step is to draw the strain diagrams. Okay, at the top we have drawn the concrete strain diagram, that is 0.003. Okay, even ACI code also recommend that the strain values are different, but for the derivations, for calculation, you have to use the concrete strain strength 0.003. And here is the strain in steel, and C is the neutral axis depth from top fiber to the neutral axis, that is the neutral axis depth. Okay, ultimate strength design, the actual stress diagram here. Okay, that is I have shown in the previous slide, that after twisting the stress strain diagram of concrete is shown here. Okay, now here comes the main part. Here why I calculated the average stress, that is basically the main philosophy given by the Whitney's Whitney. Whitney is a scientist who developed the derivations for the concrete, that is the equivalent stress diagram slash Whitney's stress diagram. Here in the previous, this is the actual stress strain diagram, here is the equivalent, okay, that is the F average. Okay, here is the equivalent stress, that is rectangular, and now due to rectangular, its first neutral axis is C, that is due to uh, the actual stress strain diagram of concrete. But when we use the Whitney's equivalent stress diagram, then the A will change, then the neutral axis depth will change, okay, due to equivalent stress diagram. Okay, so how we calculate the C and A? If we know the C, then what will be the value of A of Whitney's equivalent stress block diagram? Okay, I will show also here. Now for the Whitney's stress block diagram, okay, so first of all, D is the effective depth, then A is the total depth of the Whitney's stress block diagram. Then the center of the Whitney's stress block diagram will be A by 2. The center of the stress, definitely it's a rectangular, that will be also at center at A by 2. Here is the C. The bottom part will remain same. The tensile stresses is T, and the compressive stresses due to the equivalent stress diagram of Whitney's, that will be CC, and its location will be A by 2 from the top fiber. Now the lever arm will be LA into D minus A by 2. Okay, LA, I have calculated the lever arm. D is the effective depth. Okay, lever the centroid where the compressive force is acting, that is A by 2. So I have just minus D minus A by 2. The remaining distance will be lever arm. In ultimate strength design method, this section is always taken as correct. Okay, in the ultimate strength, we always ignore the concrete on the tension side. We only take into consideration the concrete on the compression side. C is the depth of neutral axis from the extreme compression phase at ultimate stage. From the extreme compression phase to the neutral axis, that is C. What is A? Depth of equivalent rectangular stress diagram A. Okay. Now here is again the proof of beta 1. How we can again verify the beta 1 value is 0.85, that is I have shown in the previous slides. The resultant of concrete compressive force CC acts at the centroid of the parabolic stress diagram. The resultant of concrete compressive force CC acts at the centroid of the parabolic stress diagram. It means here you can see the parabolic diagram at the center of this parabola. Okay, CC will act. Now, equivalent stress diagram is made in such a way that it has the same area as that of actual stress diagram. Thus, the CC will remain unchanged. Its value will remain unchanged, but its location will change. Okay, CC will remain same because we do not reduce the area under the curve. We have used the same area under the curve, but due to equivalent stress block diagram, the CC will remain unchanged, but A will change. Previously neutral axis is C, now due to the stress diagram, equivalent stress diagram, A is changed. How we calculate A? Now we will equate the average stress diagram with the equivalent stress diagram of Whitney. Now we will compare the average stress diagram. Okay, average stress diagram. Here is the average stress diagram with the Whitney's suggested stress block diagram. Okay, here is a F average into B into C, that is a normal way. Okay, that is a normal F average. When we take the average stress, that is 0.7 to Fc prime, the same area under the curve. Okay, F average B into C. Now the Whitney stress block diagram on the right side, here 0.85 Fc prime B into A. Okay, B into A. Now I am putting the values. F average is the 0.7 to Fc prime into C, B into C. B into B has cancelled because that are present on the both sides. Now I will keep A on one side and this value take on the other side. Okay, now this expression will come. After dividing, you will again get the value of 0.85. Okay, that is we have previously calculated. This is just again the verification of the previous method. Okay, so it means when you will just multiply C with beta 1, you will get A. The issue why we did that, because the issue was C is is the basic calculation, but A is the new one which is suggested by equivalent stress by Whitney. Okay, so what value will be the A of the equivalent stress block diagram of Whitney? So for the calculation of that, if you have the value of C, you can get the value of A but by just multiplying with beta 1. Okay, here is the factor beta 1. Beta 1 value will be used 0.85 if the concrete compressive strength is less than or equal to 28 megapascal. Now the value of beta 1 decreased by 0. Before describing the sentence, I will just explain a little bit. When the Fc prime is less than or equal to 28 megapascal, 0.85 is the beta 1. As the compressive strength of concrete increases, this value start reducing. Okay, when the value of Fc prime start increasing, this value start reducing. So value of beta 1 decreases by 0.05 for every 7 megapascal increase. 28 megapascal, when we add 7 megapascal means 35 megapascal, the value will be 0.80. Okay, in strength with a minimum of 0.65 means we can use the maximum value of 0.85 and the minimum value of 0.65. This is the equation. We can also just put the 35 megapascal, you will get the beta 1. 40 megapascal, you will also get the beta 1. Now I will discuss how to calculate the neutral axis location, means how to calculate the C and A in the ultimate conditions. Case 1, tension steel is yielding at ultimate condition, means the stress in steel is greater than Fy. If the stress in steel is greater than or equal to Fy, it means steel is yielding. Second, if the strain in steel is greater than strain at yield, if strains are so much that and the strain at greater than the strain at yield, so it means tension steel is yielding. Second case is if the stress in steel is less than yield or the strain in steel is less than yield, then that is second case, means tension steel is not yielding. Okay, what is the yield strain? Okay, here for 300 grade steel and for 420 grade steel. We already know the modulus of elasticity is stress over strain. Okay, now I have just interchanged strain Y with E. So for grade 300, 300 megapascal divided by 200 into 10 to the power 3 megapascal, the value is 0.0015. And for 420 grade steel, 420 divided by 200, 200,000, so value is 0.0021. So that is the yield strain of steel. If our strain in steel is less than yield, so that is the second case, and if our strain is in steel is greater than the yield, so that is the first case. So let's start with the first case. When tension steel is yielding, means at tension stress is Fs. Okay, if Fs is equal to Fy, so that is the first case. Means area of steel. How we calculate the force? Basically the basic formula of pressure, same way, pressure is force over area, or stress is equal to force over area. So to calculate the force, we multiply area with stress. So similarly I did here. Tensile stress, okay, tensile stress is Fs. So I have just Fs multiply with the area to get the tensile force. So tensile force is As into Fy. In the concrete side, that is equivalent Whitney stress block diagram, that is 0.85 Fc prime into B into A, and the lever arm is the D minus A by 2, that is I have already discussed. Okay, so here for equilibrium, for as we know, as the loading start increases, the internal force equilibrium will remain maintained up till the failure. Okay, so T is equal to Cc. Here T is As Fy and Cc compressive force, that is 0.85 Fc prime into B into A. Okay, you want A because at the start I have discussed. Now I will show how to calculate the neutral axis depth. Here A, the rest of the part I have divided on the left hand side, so you will get A. So if you get A, you can calculate C. How? You already know A is equal to beta 1 C. If you have the value of A, then you can calculate the value of C, because you already know beta 1 is a constant value. So now you have calculated the A, and in the lever arm you can put A and you can get the value of lever arm. Okay, so again the basic formula of the couple, nominal moment capacity depending upon steel, you can calculate T into LA or Cc into LA. Both way is okay. So T value is As Fy and LA value is a lever arm D minus A by 2. I have just put the values. Now that is a nominal capacity. Now I will put the phi factor. What is phi factor? In the ultimate strength design approach, I have already told you the major part of factor of safety is applied on loads, and the minor part of factor of safety is applied on the material. So that is all I have discussed. The derivation is, that is the material property. So here is the reduction, smaller factor of safety, that is a phi. Okay, that's why it's a design moment capacity. Now nominal moment capacity Mn depending upon concrete, previously that is on steel, Cc into La. Cc value is 0.85 Fc prime B into A. The lever arm is same. You can use either formula, either this formula or this formula. You will get the same moment capacity by both formulas. You can use either formulas. This is the general procedure for the calculation of neutral axis depth and moment capacity. Now the information about the minimum depth for deflection control. What depth you will use minimum for the design of beam, so that is the deflection control. Deflection is inversely proportional to the moment of inertia. Okay, here is the moment of inertia. For example, rectangular section, that is B and that is a D, then moment of inertia is B D cube over 12. Deflection depends upon span, end conditions, loads, and Fy of steel. All things are things matter, but the one most important for the design of concrete beams, that is the depth of the section. So if the depth of the section is more, then the less deflection will appear. Okay, here you can see BD cube over 12 in the moment of inertia. If you have a large depth, okay, then you will get the more moment of inertia. When you have the more moment of inertia, you will get less deflections. Here is an example of moment of inertia. For example, here is a steel. For example, here steel ruler or steel scale I have shown. If you put the steel scale in this way, okay, then you will get more deformations. You can try okay, at home, at your university or school, etc. When you have a scale and you have put in this direction, uh, you will apply the load at the center of the scale, you will see the large deformations. And if you put the scale in this way, okay, vertical side, and then you will apply the load, then you will see that there will be less deflection, or you will see negligible deflection. Why? Because the edge or the height property matters a lot in the design of beam. Okay, so now here is a minimum depth for deflection control as per ACI. If you have a member, for example, that is a solid one-way slab, now we are discussing beams. For example, if we have a concrete steel grade of 420, then for simply supported we have to provide L by 16 minimum depth. We can provide more depths, but that are minimum. Similarly, for cantilever, that is L by 8 for 420, and L is the effective span of the beam of or the slab, okay, for slab for the beam. So that's all. Have a nice day.